All right, welcome to Fluid Mechanics, MAE 335. So today, for this particular lecture, I'm going to talk about why we're studying fluid mechanics and what I think is difficult about studying fluid mechanics. We'll do a little bit of introduction to the structure of the class, and then we'll end this video, and I'll try to chunk the video lectures into small little bits, and in future videos we'll start getting into some more of the content. So yeah, let's talk a little bit about the class structure here. So if you look at the syllabus, the structure of this class will be that we'll have a lecture that'll be videos online. So it'll be online recorded lectures, which is basically me talking at you and you filling out scaffolded notes. Yeah. So, what are scaffolded notes? Well, for every lecture, like I said, I'm going to break the lectures up into smaller bits, so they're not going to be 45 minutes long like they normally would be. There will be an outline that I'll post, and then I will also post the full filled-in notes, right? And so what I'll be doing is I'll be talking through filling out these scaffolded notes, and then you can fill it out alongside me as you go. Yeah. There will be in addition to the online recorded lectures, there will be what we call synchronous. One thing you're going to find out about me is I can't spell at all. Let's add a couple O's and use an S's in there. Synchronous lectures. This will be more akin to office hours. So I will be. We'll hold Zoom classroom. I will try to come with some problems for us to do during this time. I will we'll also do some group work. I think it's very important to work with other people on this kind of material. If you look at the research on learning, what you generally find is that there's two things that help you really learn material really well. One is spending time with the material. It turns out it just takes a lot of repetition in order for things to stick, right? And the second is, though, the quality of the time that you spend with the material. And what makes time quality time is when you're engaged in the material. So if you're sitting in a lecture and you're taking notes and you're furiously writing down word for word what the professor is saying, you're doing a good job. Yeah, not too bad. That's not the type of engagement we want, though, right? So as you learn fluid mechanics, what I want you to practice is working to reinterpret the material, right? So if you're taking notes, for example, this is the easiest way to speak about it. So if you're taking notes, don't write down what I say. Listen to what I say and then try to rephrase it in your own words, right? Don't just copy down the figures that I write. Change them a little bit so that every time that I write something down, you have to think about how does this work with your figure. And that kind of engaged thinking is priceless. I read some psychology research, maybe it was cognitive neuroscience research, but anyway, they talked about how if you do that kind of engaged note-taking, you can study 60% less than somebody else and still essentially score as well on the exams. And if you think about it, that's an incredible amount of time that you're saving every week. So use this lecture time, well, whatever this lecture time is. Hello 2020. But use it well to be really engaged when you're doing the material. So that brings me back to group work, right? So during our lecture times, I'm going to try to get you guys to be as engaged as possible. Now, if I were there in front of you in person, I would be not clapping. I'd be doing things to try to keep you awake. I would constantly be asking you questions. I will be asking you questions in these lectures as well, but it's different when you can kind of ignore me because I'm not looking at you, right? So what we'll do during these synchronous lectures is I might bring a few extra problems, or we might look at problems that are in the notes, and I'll set up breakout rooms in Zoom, and you guys will work on them in groups, because when you're talking to people about doing work, you are engaged, right? You can't help but be engaged unless you're the one that nobody wants in your group, right? Because you're just regurgitating stuff that is not pertinent to the situation. Cool. So that will be our lectures here. We're also going to have a recitation. In the recitation, we're still working out the format of. Traditionally, you would go into class. We'd have some problems prepared that the TAs would do with you, and then you could ask questions about the homework and such. We're not quite sure how the recitation is going to work in the era of COVID. At a minimum, I think we're going to have, well, we're not sure what kind of technology our TAs are going to have either. So we'll get back to you on the recitation. Let's put a question mark there for now. But for the most part, it'll be review and practice of the material. We haven't figured out quite how we're going to do that. We're going to have exams. And the exams are going to be evenings. They'll be 2 hours long. And we're going to set up, I believe, to prepare for these exams, what I'm going to need you to do is make sure you have internet access and a computer with a webcam. Because what we're going to do is we're going to have everybody log into a Zoom meeting so that we can see your face and see that you are present, right? And we're periodically going to message people and talk to them just to make sure you're really there and not just showing us a video, right? That way we can make sure you're not cheating, basically. And then we'll have you upload. So we'll make the exam available to you. You'll take it in front of us. You can ask us questions through Zoom. We can also push updates about the exam and answer questions everybody would care about. And then you'll scan it, take pictures with your phone, whatever, and upload it to a folder for grading later. We'll also have a final exam. It has not been scheduled yet as of the recording of this lecture, but it will be the same format, but it'll be longer, right? We have, I believe those are 3 hour long exam. And the final exam is it's cumulative. Yeah, it's cumulative. It's a cumulative final exam. So we're also going to have homework in this class. We have online homework through Wiley Plus. And we'll have information about that on UB Learns. And we're also going to have written homework. So written homework will be due weekly. And so will Wiley Plus. And this will be turned in, and this will be turned in through learns. And something we do with the written homework is there's a writing prompt attached to every single one of these. This has a writing prompt. And this writing prompt is basically going to ask you about what parts of the homework you thought were difficult and what parts you thought were where you got stuck. And it's going to ask you to think critically about how well you think you did at the homework. And the reason for this writing prompt, right, is the same as the group work and the same as the scaffolding notes. It's to get you to think critically about what you've done. So we did this last year, and then we got some feedback about it, and about 1 in 20 people said the writing prompt was incredible. They learned so much by trying to write the writing prompt. About 10 out of 20, so about half the people said it was useless. All they did was write the same thing every week. And then there was a couple like weird comments in there, and some people didn't comment on it at all. The pattern, of course, is that the people who spent the time to actually think about where they got stuck and why they got stuck got a lot from the writing prompt, right? And the people that just did a perfunctory kind of not copy paste, but almost copy paste, because we ask you to circle the portion of the written homework where you got stuck, where you had a problem, where you think you did really well. Those people didn't learn anything because they didn't spend any time on it and they weren't engaged in it, right? So hopefully the lesson of this is we're giving you lots of opportunity to do engaged work, to really use your time in this class well, and I hope you guys take it. We'll see how it goes. Great. So at this point, I'd be like, "What questions do you have?" And you'd say all kinds of questions, and that'd be great. But we don't. That's not going to happen, and I'm sad. All right. So let's move on though to why are we studying this? So most classes you take. This is a frustration of mine that I have. Most of the classes you take have this structure. We have a very well-defined problem that the professor poses. Even if it seems confusing, trust me, it is a well-defined problem compared to what you're going to get for the rest of your life. And then you're asked to come up with a solution. You're asked to come up with a solution. And this is essentially my responsibility, and this is your responsibility. Let's just go with you. And it's nice and clean, right? In the real world, though, and let's be clear, academia is the real world. It's just us. We're holding your hand an awful lot. In the real world, you're going to have to come up with. In the real world, you do have to do all these steps to solve a problem, right? You have to identify a need, make what we call a poorly defined problem, right? Do research, figure out a well-defined problem, and this usually means some kind of engineering language. So this poorly defined problem is like, I don't want to spend so much energy to get to work. A well-defined problem is I only want to move my foot and my arms, and that means I have to design a car. So you go from a well-defined problem to a conceptual solution, and then you have to figure out a detailed solution, materials, processing, dimensions, all those things. In reality, most of the classes you have, the professor has done all of this work here, right? And you're just expected to do this work right here. Come up with a detailed solution. And the reason for that is most introductory jobs that you're going to get, they only really trust you to work on detailed solution stuff, because a lot of these other things like determining needs and poorly defined problems and well-defined problems are incredibly difficult to do well, and they take a lot of experience. I have a friend whose company does a lot of contracting work where all they do is this part of the problem right here. companies will call them up and say, hey, we need you to create a well-defined problem for us, that then they will contract out to a completely different company to actually solve, right? So all of these steps are very difficult. And what's difficult about it is you're going to have to do all of these parts at some point, right? You'll have to define define some kind of need. Depending on how small the company is, you might also have to develop a poorly defined problem and a well-defined problem. Or go from a well-defined problem all the way to a detailed solution, right? And the truly difficult problem is this isn't a unidirectional process, right? Like, you get to a well-defined problem, you get to a conceptual solution, you're like, oh, well, this isn't going to work. We have to go back all the way to a poorly defined problem. Or, you get to a detailed solution and you find out that the manufacturing process you thought isn't producing the results you need, so you have to go back to your well-defined problem. Or back to your conceptual solution and figure out what you can do. Design is iterative, right? And this is really what we're describing as a design process. The part that we've traditionally taught you in this class, like I said, is this part right here, where we take well-defined problems and we use a model. We use a model to get a solution, right? So, in general, one of the takeaways I want you to take from this class, because we don't use this language very much, we talk about, like I said, we talk about what we traditionally teach you as if this was engineering here. We pretend this is engineering, and it's not. It's a small part of engineering. But we use these models to predict how systems will behave. Right? So, what's nice about the way classes are traditionally taught is that a lot of these models that you use to predict how systems are behaved are connected in a lot of ways, right? So, if you guys take solid mechanics, right? All the models you learn are related to each other, and they get progressively more complicated. But in general, what you learned at the beginning of the class is somewhat useful at the end, right? Fluids is quite difficult because that is not true. The models we learn are disconnected. Oops, disconnected. So, what does that mean? It means that fluids is subtle, the behavior is complex, and because the behavior is complex and varied, we need lots of different ways of predicting how systems will behave based on assumptions we can make about that system, because there's no one way to tackle all of fluid behavior. Okay? So our models are disconnected. So what we're going to do is we're going to learn something, and then we're going to need it later, but our future models are not going to build upon it, right? So you're going to have to learn a whole new system, a whole new set of assumptions, and a whole new set of math. Ooh, which brings me to point number 3. The math is not trivial. You will have to do integrals and derivatives and that kind of work. And more importantly, the mental not the mental math. We're not just doing adding and subtracting, but the setting up of the math is not trivial, right? So we're going to ask you to integrate across an area, and you're going to have to understand what an area integral is, how to set it up, what area we care about, and what kind of directions matter for the problem. So the math is not trivial. So these three things put together make fluids very difficult because, like I said, we're going to have about 6 or 7 sections of this course where you're going to learn something and then we're going to start something new, and you're going to be like, whoa, hold on, I'm like 80% of the way to getting this thing. And we're going to be like, oh, got to move on, right? Which is why the writing prompt, which is why the group work in class and the scaffolded notes are so important. You need to spend the time early to make sure that you are not falling behind, because once you fall behind in this class, it's very difficult to catch up. You have to work twice as hard to catch up. You can't just pick things up later because we're reviewing them because we need them still. No, we're moving on to something completely different. Yeah, so you have to spend the time on this class. A consequence of this is that since models are disconnected, knowing which model to use is quite difficult, right? In some of your classes, you have since the models are connected and are used to tackle progressively more complex systems, you kind of know what to do based on how complex the system is, right? Like based on the information you're given, right? Like again with solids, if you're suddenly given the shape of the beam, you know you have to deal with the oh shoot, I forgot what it's called. Area moment of inertia, is that right? Oh, it's been like 20 years since I took that class. Anyway, it's not immediately obvious based on the information we give you for a problem what model you're going to have to use. So something I've been working on incorporating into this class is what I call a semester-long design problem, where we're going to show you how each thing we learn can be used towards a design problem, right? And then how those that information, how the tools we have are specialized and what part of the design process they're useful for. Okay, so let's talk about this design problem. It's a beautiful, beautiful problem. So let's draw it here. I'm going to draw a little lake. Pretend this is Lake Erie. Put water in it. Water there. One thing you're going to learn about in this class is, we're going to learn the very basics of rocket science, if you will. If you push something in one direction, right, you go in the other. So one thing we can do is we can potentially build a space tower out of water jets. So we're going to take a long tube, put a little platform at the top, come down like this, and we're going to put water jets on it. Like this, shooting water down and forcing a platform up so we can get somebody as close as possible to space. So let's pretend this is space there. Little moon, little stars. If you think about it, this is going to be an utterly fantastic thing to view from the distance. This is going to be ideally miles tall, right? And the volume of water it's going to be shooting out, and it's going to shoot out the water very fast, right? Because the faster you shoot, the more force you get. So we're going to want to shoot the water out really fast. And it's going to produce this giant cloud, and you're just going to see this miles tall sheet of water vapor and clouds just appear out of nowhere, and it's going to produce an incredible amount of sound. Anyway, it's fun to think about. So we're going to try to design the space tower, and we need to think about what do we need this space tower to do. Well, at a minimum, this space tower is going to have to support the weight of one person. 2, withstand wind, because as it's rising up, right, we're going to have wind that might be pushing it sideways, and it has to steer itself, basically. 3, we don't have infinite power here, so it cannot consume too much power. It must be buildable. We can't use exotic materials, basically. and it has to get as high as possible. So what things do we need to predict in order to solve this problem? We would need to predict how much thrust each nozzle will produce. By the way, these are cursive Z's. You can look it up online. 2. How thick does our pipe need to be? Three, how much power does each pump require? And how many pumps? And what arrangement are we going to put them in? And 4, how much drag will the tower experience? And we will learn models to answer all of these questions. Models that will help us predict the behavior of this system so that we can answer it. So, for example, question 1, we can learn with Bernoulli's and conservation of momentum. B, or 2, I mean, we're gonna tackle with fluid statics, and also with Bernoulli's. You're gonna find out why Bernoulli's is so popular, because it's dang useful. 3, we're gonna learn with internal flow and conservation of energy. And 4, we're going to learn with drag and lift. They're pretty related. And then we're also going to do a bonus section which is the question of, should we even work on this? And we're going to use dimensional analysis to answer that question. Great. All right, so we're going to stop now, and then we'll tackle dimensions and the next set of material in the next lecture.